Well, hello, everybody. I'm Matt Lungren, and I'm the co-director of the Artificial Intelligence and Medicine Imaging Center at Stanford University and associate professor in the Department of Radiology. I'm going to talk today about applied multimodal data fusion for medical imaging at the point of care. So when we think about medical imaging projects, we often think about sort of very pixel-based analysis, right? So here's an example of a 3D imaging exam, so a multi-slice CT of the chest, which was performed to evaluate for pulmonary embolism, which is a dangerous condition that is often very important to identify. And there are many solutions on the current market even for this problem, for automatic identification using the pixel data to identify this condition. And it's an important problem to try to solve. It is something that is increasingly problematic for the healthcare system, at least in the US, as these studies are often very expensive and resource intensive and are frequently ordered in a variety of conditions that present looking like pulmonary embolism, but actually in fact turn out to not be. And so it has become a very much important type of examination to consider around either automatic identification of this disease or potentially reducing the number of studies that are done for this purpose because of its strain on the healthcare system. And in fact, this has been a focus of legislation recently to identify pulmonary embolism. And of course, the CT examination example that I showed you is exactly the study that's used to identify pulmonary embolism. There's been a lot of work to try to reduce the resources necessary to make this diagnosis. And so we sort of sought to create a 3D kind of model to look at this problem because, again, it's a multi-slice problem. So just as many groups do, we focused on building a supervised modeling approach that could identify pulmonary embolism with high degrees of accuracy at the expert level. And the existing approaches in the literature, they tended to use extensive, computationally expensive pre-processing and feature engineering, which were kind of over-engineered and really not capable of end-to-end inference in a clinical workflow. And so an important component of this was leveraging a 3D model as opposed to a 2D model. And it was pre-trained in this case on Kinetic 600, which is a very well described, basically the ImageNet for video, in order to create a model that had initializing weights to move forward in sort of analyzing these types of studies in a 3D fashion. And we needed to explore this computationally inexpensive solution that could digest the entire exam series. Our key insights were focused on the squeeze excitation network, which happened to have won the most recent ImageNet challenge. And then, of course, again, as I mentioned, the pre-training on a 3D video series. In case you're wondering, the squeeze and excitation networks basically have these building blocks for CNNs that improve the channel interdependencies at very little to no computational cost, which was important for us. And again, they were able to achieve state-of-the-art on the ImageNet challenge, beating the best result by 25%, which again, it was fairly significant for that challenge. And the network weights of each of its channels, it weights each of the channels equally when creating the output feature maps. And so these blocks are all about changing this by adding a content-aware mechanism to kind of weight each channel adaptively. So it's quite an efficient approach. And this was work led by Mars Wang, who's a PhD student in my lab. And so our result was phenomenal for this work. We were able to come up with both state-of-the-art performance on Stanford PE studies for identification, as well as an external validation data set at another hospital where we did not obtain training data, but then applied to a test set. And we even built, as you can see here, just a simple visualization tool. And all this was done in a very short period of time. As this is not a surprise to most of you in this audience, it is certainly possible to create a given use case and generate a model that can do it in an automated way. We also made this data available for the RSNA challenge after publishing this in one of the Nature journals. And so you can actually go and access highly curated, annotated pulmonary embolism CT data, annotated by expert imagers, subspecialist radiologists, and that was part of the 2020 RSNA pulmonary embolism challenge. And this data is from several countries and 4 institutions and comprises more than 12,000 different CT studies. So it's the largest data set of its kind, and had more than 80 expert thoracic radiologists as annotators. Eventually, we had 784 teams from around the world that participated in this challenge, and the top 10 teams, many of which open source their solutions. So basically what I'm trying to paint a picture for you here is that we've really have a great mechanism and system as a field right now for creating a clinical use case, potentially making the data available, but at the very least being able to build models with the flexible tools that we have available to us in the community to address pixel-based medical imaging problems. But what I want to talk about today is the concept that medical imaging is more than pixels. And this is actually lost on a lot of what you're seeing in the field right now and in general. When physicians who are trained in imaging, like myself, look at an imaging study, we don't just look at the imaging pixels alone. Now, we do a lot of other things. We actually tend to take in all of the clinical context and the information surrounding the situation that led to this exam being done. And the reason there's a gap is that currently we're seeing most data sets don't include that information. So the companies and many of the groups that are working in the space have focused on almost uniquely just on the pixel data. But as we know in the field, we've known for years since our field began that medical imaging data is incomplete without contextual information to make the best diagnosis. And this plays into issues around robustness. It plays into issues around deciding on what diagnosis is important. And this is not just in imaging in radiology, at least. This is in other specialties that use imaging, like pathology and ophthalmology and dermatology. We need clinical context and data to ultimately make the best decisions. But as I've just shown you, we can easily create state-of-the-art performance in a retrospective fashion for pixel-only tasks. And when you see these benchmarks that compare to human experts, that again is often done in a situation where the human expert also is not given the clinical context. And the challenge there is that you're actually creating an artificial environment that does not reflect real practice. And so what kind of other information do we have? Well, in addition to the pixel data, the things that we rely on, I've listed here, and this is just the types of EHR data that we would use for the pulmonary embolism use case that I just pointed out. And so we actually set out to say, could we create a model based on the contextual information, not the pixel data, that could do the same task as our pixel model? So in other words, can we take all of that EHR data and use it as clinical context for a given patient and predict whether they likely have a pulmonary embolism or not? So we actually created a prediction model, again, based on patient timelines. So over time, what does their EHR data look like? And with some feature engineering, sort of set up a pipeline that allowed us to look at various approaches, including neural network models, elastic net, which is sort of a regularized regression, which sort of combines L1 penalties of lasso and L2 penalties of ridge to overcome some of the limitations in high dimensional data that have a relatively small number of samples, at least in relationship to the number of features. And this is all very common practice in sort of the EHR, both structured data and even some unstructured data work. But the goal, just to make clear, is to take a contextual information, create a model that can predict the likelihood of pulmonary embolism without the pixels, and then help us decide, does this person need to be imaged or not? If they're low, they don't. If they're very high, maybe you start treatment as opposed to waiting for the result of the imaging exam. So this model has utility in and of itself, independent of the pixel data, and this is work done by Iman Banerjee. And so to look at this, just like we do with our other models, we wanted to see how our performance was against what our traditional rules-based or scoring systems that humans would use. And we found that in the Stanford healthcare system, where the model training data came from, the neural network actually performed the best. And we also did external validation, just like in the other case, in this case with Duke, and found that the model was robust to external validation. So again, this is a clinical context model. This is not pixel, but it's performing a task that typically requires pixel data to make the diagnosis. So there's a lot of excitement here. Why? And by the way, we published this in JAMA. So why is this important? So we can actually integrate this system into the existing workflow where a patient comes into the emergency department. They may undergo a traditional scoring system to rule them out for the disease, but our perform model could actually come into play here in the moderate to high risk and help triage patients as to whether they need imaging or not, based on, again, the contextual data around that patient. And we found that we could reduce this imaging study, the need for the imaging study, the need to get the pixels, we could reduce it by up to 20% without increasing the false negatives and causing potential harm. So this is very exciting. So what does this mean? Well, let's just think about this now. We have a vision model, as I told you, that had fairly good performance, that looked at only the pixels. And now we have an EHR model that only looks at the clinical data or the context. So you probably understand where I'm going with this. Here's an opportunity for us as a field to try to match what human experts do and use the pixels and the clinical context together to make the best diagnosis. And so we actually did some literature search and actually ended up doing a full analysis of the literature that we published in Nature that sort of described the best practices around fusing multimodal data in order to solve an important clinical use case. And so how does this work? Well, we tried to be very prescriptive in the sense that we took different approaches and came up with some terminology. And I invite any of you to take a look at this paper and see how it might apply to your work. But in general, as you'll hear from some of the other speakers, we have early fusion, joint fusion, and late fusion. We try to categorize these. And the early fusion is really where you're concatenating the original features or the feature representations at the very early input level with a single feature vector before feeding into the machine learning model for training. And that's kind of, you can see that there where things are being concatenated early on. Joint fusion is kind of in the middle of the extremes where it joins the features at the input level, but the loss is propagated back to the feature generating model, or intermediate fusion, which has this join learn feature representations from intermediate layers of neural network models with features from other modalities as input to a final model. So you can kind of get a sense that there's a couple different approaches of this joint fusion. While at the other end of the spectrum is this late fusion, where you aggregate results at the decision level, very similar to an ensemble, but this sort of leverages predictions from multiple models to make a final decision. And so just having that sort of common language and understanding of how multimodal data fusion could work, you can imagine that you could take clinical context or clinical data and pixel data and go through a variety of these different approaches to training a unifying multimodal model to figure out which one works the best for your use case. And so we tried this with our project where we had the CT imaging data and we had the EMR data, and we tried several different approaches. And we've actually ultimately found that the late fusion in this particular case worked the best. But we did actually improve the model. Having that clinical context really did make a big difference for us, and our fusion model reached state of the art. And again, this is an end-to-end solution, which is even more useful for a clinical context. And we looked in and found some examples of where the pixel-only model was wrong, but when it had the clinical context, it was actually more accurate. And again, we published this work most recently in Scientific Reports. You're welcome to again check these out. All of these are open access, by the way. So where does this go from here? Well, it turns out that in a lot of our work, we're getting a lot of interest from clinicians who are interested in using these models, not radiologists, but actually frontline clinicians who want to try out these models at the point of care when they're taking care of their patients. Why is this interesting? Well, as it turns out, in our current healthcare system, the way things work is that you go and see your doctor, and that doctor orders imaging tests. And then there's this period of waiting where they're waiting for the results from the radiologist to tell them what's going on. And that's because the radiologist is very busy. So in most cases, the applications that you're seeing for deployment and clinical translation for AI in radiology has really focused on trying to make the radiologist more efficient, so reducing the time it takes them to go through the studies. But what we've decided to do, and what we've found, is that there's a lot of interest from this doctor instead. This doctor could use the tools and actually make decisions right at the point of care if we can provide a contextually aware AI model, in this case, maybe the multimodal data fusion approach, that allows both clinical context and pixel data to inform clinical decision making. And so this is actually the basis of a project that we started with here. This is me meeting Nat Dean, who's the chair of pulmonary critical care medicine. So he's a pulmonologist, not a radiologist. And he's created a tool that uses EHR data to help clinical decision-making around pneumonia. And how does this work? Well, this ePneumonia tool relies on, again, sort of contextual data from the EHR, but also needs to have some of the information extracted from the radiology report of the X-ray, as you can see here. And so what this is essentially is doing is this is kind of a hack around a multimodal data, whereas it takes the report from the imaging studies and not the pixels themselves, which requires a human to create, and then extract structured data from the report in order to create a model that actually can help do clinical decision making. And so when he tried this out in a small pilot, he was able to reduce 30-day mortality in this country for pneumonia by 30%, which is astounding, right? To reduce 30-day mortality by the use of this clinical decision support model. But the problem was that the MD utilization, so no one was really using it. The utilization was 20%. So why was this? Well, it turns out, as I was trying to tell you earlier, that there is still a reliance on the radiologist because this model does not consider the pixels. It considers the report, which is generated from the expert radiologist. So they still have to wait for the radiologist to interpret the exam. And in some cases, that could take up to 6 hours. So no one's going to wait for 6 hours before making a decision whether to treat a patient. So we've actually inserted an AI model actually as a multimodal fusion model, similar to the approach I talked about earlier, where we're taking, this is actually an early fusion approach. We're taking EHR data that he's already kind of developed and the pixel data together and creating a model that can make a decision right away without having to wait for interpretation. And so the advantages here at the point of care, as opposed to deploying this in the radiologist's room, is that they don't have to wait for a radiologist. They don't have to rely on free text, as is common in some of these problems. And there's no variability that consistency actually helps this model be more useful to the practitioner. And so the given physician on a given day is no longer a consideration. And what we found was in our analysis that our model actually performed as well as physicians for the purposes of analyzing the pixel data. So we felt that the pixel model alone, and then when incorporated with the EHR data and multimodal fusion, we were able to perform at the level of human experts. And this is work done by Jeremy Urban. And so our clinical trial, which is now ongoing in 55 clinics, is actually looking at the difference in outcomes at the point of care with the use of this tool in the workflow. So a multimodal data fusion model that is taking in clinical context and the pixel data to help make a clinical decision. And this is currently funded by the AHRQ. But if we take a step back, we can look at a larger opportunity. So we can see that most of the world, and is often a surprise to American audiences, that most of the world doesn't live in North America. In fact, only 5% of the population of the world lives in North America. So where are we there in trying to address where the population is in their needs? Well, there's a lot of focus on U.S. healthcare, despite the very little of the world lives here, because of the amount of money we spend in our economy for healthcare, and that makes sense from this perspective of someone trying to sell a product. But when we look at impact, we recognize that most of the radiologists in the world aren't in the places where the people are. So there's a huge opportunity to provide access to models like these at the point of care in situations where there are no radiologists to begin with, and the impact is potentially huge. And so when we look at the question of whether AI will replace radiologists, it's actually that clinicians who use AI may replace radiologists or may substitute for radiologists who aren't even there. And we actually tested this out with another multimodal data fusion project. Again, we really need to think about not just the pixel data, the features in the pixels, but the clinical context. And here's a situation where we worked with pulmonologists in South Africa to create a multimodal data fusion model that could identify tuberculosis amongst a host of other problems in HIV positive patients. And because of the fact that they don't have radiologists that are able to staff this clinic, it was a critical need for this group and this patient population, because what was happening is the pulmonologists, who are not imaging experts, were trying their best to interpret the x-rays to make this diagnosis. And so again, we created a model that took in clinical information and the pixel data and created a probability for the presence of tuberculosis so that these physicians could treat these patients. And so this model, which is, by the way, currently available right now on GitHub, you're welcome to explore this, allowed us to present the model to the clinicians right at the point of care in a situation where there weren't a regular radiology group that interpreted for these people. And this is work led by Pranav Rajpakar. So just some quick headline views of this. We found that the clinician performance without assistance was relatively low, below that of a South African radiologist, but this is a very hard task, and I actually took the test myself and found that it was incredibly hard. We don't treat tuberculosis at all in my practice, so it was a new diagnosis for me and very difficult. But we found that with the model, the multimodal data fusion model, together with the clinician, they were actually able to exceed the performance of a South African radiologist, which is tremendous, right? Imagine the opportunity here for these types of models to be deployed and to assist people at the point of care. So it really is a different paradigm shift here. So, that was kind of a whirlwind tour through just the concept of really just to help all of you think a little bit about what else beyond the pixel will help us achieve the standard of care. And when we have achieved the standard of care, where in the healthcare environment do we apply or deploy these models? And I hope that this gave you some new opportunities to think about, both from a global health perspective, but just also in general, workflows that can enable different parts of the healthcare system to leverage these robust models that take in pixel and contextual information to make decisions. So I hope that this was instructive for you. Thank you so much for attending, and please reach out if you have any questions. Thank you.